right? So the dot product gives a scalar as a result. Cross product gives a vector. And to be able to describe the vector in a precise way, we have to describe both its direction and its magnitude. So we basically do this is the definition, it's just a reminder. So A cross B is a vector where the direction is found by the right-hand rule, but in particular, it's perpendicular to both A and B. There are two possible directions which are basically perpendicular to A and B. It's basically that direction or the other one. So to find which one is it, we need to use the right-hand rule, right? That's just a convention. We just define the cross product in such a way that the right-hand rule, by using the right-hand rule. Okay. The second one is that the magnitude is given by some certain relationship. So it's basically product of the lengths multiplied with sine theta, or we can actually geometrically equate it to the area of the parallelogram formed by these two vectors, right? That's another way of looking at it. In any case, let me also tell you that yesterday's lecture, I have drawn this in an incorrect way. So the picture was actually unambiguous as a three-dimensional picture, but instead of B cross A, I have written A cross B over there. In any case, this picture is correct with the right-hand rule, all right? Just keep this in mind. Okay, so associated with all of these, we have these. So B cross A and A cross B, they are not same. They have equal magnitude, but they have opposite direction. So therefore, that's the first thing that we have said. So A cross B is equal to minus B cross A. So this is an anti-commutativity. Let's remember this. Moreover, we have these. A cross A is equal to 0. So the cross product of a vector with itself is equal to 0. But that's just a special case of general relationship. So A cross B is equal to 0. Let me say it like this. This is if and only if A and B are, let me say it like that, parallel or anti-parallel. Okay, that is one way of understanding if two vectors are parallel to each other, parallel or anti-parallel to each other. Take their cross products. If it is 0, then that's the case, right? You can actually think of it like that. So parallel means, or these actually mean that the vector, one of the vectors can be expressed as a scalar multiplied with the other one. Okay, they have same or opposite direction, but only their magnitudes are different. Okay, you can also think of it like that. In any case, so let's box this. All right. So the next one is basically, I'm just going to write it down like that. All right. So I cannot prove this. I can prove this, but it's just a three-dimensional thing. It's the distributivity of the cross product. Right. So, and that's an essential property. That's basically what makes it a proper algebra, actually. So that essentially means, as long as you just note this important rule that they don't commute, you can use the ordinary algebraic rules for actually doing the cross product. Okay, that's essentially what it means. So that's distributivity. Distributivity over addition, basically, right? So that's anti-commutativity. Let me write it down like that, right? Anti-commutativity. This is distributivity. There is no associativity, right? Let me just say it like this, but I'm not going to prove this, right? I can give some examples later. So that's not true. A cross B cross C is not the same thing as A cross B cross C. Okay, and the reason is that, I mean, you can think of it like that. So this vector, for example, we know that has to be perpendicular to A. It also has to be perpendicular to this other vector in here, whatever, but it has to be perpendicular to A. The right-hand side has to be perpendicular to A. But the left-hand side doesn't need to be perpendicular to A. It has to be perpendicular to this one and to that one, and probably it is not perpendicular to A, right? So they are not equal, so that's not associative. Okay. I mean, it's important, right? Let me just make this bigger. So as a result, if you have the cross product of three vectors, you don't write down an expression like that, A cross B cross C. So that's basically ambiguous. I mean, I would even count this as some nonsensical statement, right? So if you have this kind of an expression, you have to specify which product is evaluated first. A cross B can be equal to B cross A only if it is equal to 0, only in that case. Right? I mean, this is something that you can, this is just a vector equation. You can actually easily solve these kind of equations. So these are fundamental, these are vector identities. That means that they are valid under all conditions. So, I mean, under some circumstances, that might turn out to be equal. For example, if one of the vectors is 0, that's the case. But I mean, when I write this thing down, I'm basically saying that this is usually the case, okay? So in any case, so the next thing is basically the cross product of the coordinate Cartesian unit vectors. So cross products of Cartesian unit vectors. Okay, let me remind you again the essential things in here. So we have an XYZ frame. We are going to use these frames a lot in almost all physics courses, probably, all right? So these are perpendicular, mutually perpendicular to each other, right? Just keep this in mind, but I'm not going to draw these lines in here. So let me use a different color in here. So the unit vectors, I, J, and K, these are the unit vectors along these three special axes, okay? So we would like to find, for example, I mean, there are certain things, for example, I know that I cross I is equal to 0, right? And similarly, J cross J, because the cross product of a vector with itself is equal to 0. All right? So that's okay. I mean, these are the ones that, I mean, this is like, in a way, the opposite situation for the dot product. So for the case of dot product, I dot I would be non-zero and it's equal to 1. I mean, these dot products would be equal to 1 and all the other dot products would be 0. In the case of cross product, they have just changed places in a way, right? So the same vectors have cross products which are equal to 0. So these are obviously true. Now, we would like to find what I cross J is. Okay. So I can first talk about its magnitude. Yeah, let me write this thing down. I can talk about its magnitude. I can say that the magnitude is basically the magnitude of the, let me write it down like that. It's the magnitude of the I unit vector multiplied with the magnitude of J unit vector multiplied with the sine of the angle between them. And this time the angle is 90 degrees. So these are unit vectors. So all the magnitudes are 1. The sine of 90 degrees is equal to 1. So therefore, the result is has a magnitude 1. So that means the result is also a unit vector. Okay. Then we ask about the direction. Sorry, let me write it in here. So direction. Okay. So basically I and J are in the XY plane. So therefore the direction should be perpendicular to the XY plane. So the K unit vector is the Z axis is perpendicular. So therefore the result is either plus K or minus K. Okay. Again, there's this two possibilities in here for the perpendicular direction. But the question in here is now that which sign should I take? Okay, so I cannot answer this question without knowing in which way the z-axis is drawn, right? So in any case, we actually make a convention here. We just choose the XYZ, the z-axis in such a way that the +1 is the correct answer in here. Okay. So in any case, let me say it like this. So that's the convention. The XYZ frame is always chosen as a, let's say, right-handed frame. This is the expression that I'm going to use. Whenever necessary, I'm going to, whenever necessary, I'm going to remind you this. But usually we choose it, right? We choose it. Let me not say usually, always we choose it like this, right? That's the convention. But in any case, let's continue. The XYZ frame is always chosen as a right-handed frame. Let's say so that I cross J is equal to plus K. Okay. So as a result, the answer to that question is basically plus K. Right? It's a unit vector perpendicular to both I and J, and well, the minus sign doesn't apply. So again, what's a right-handed frame? I mean, we can use our right hand to actually see in which way the frame should be established. Right? I'm going to draw my right hand again. Right? All right. So the thumb. Again, we use the first three fingers. I don't think that there is another way of actually understanding the sense of a reference frame, right? It's something like that, right? Okay, so again, first finger, second finger, third finger, all right? So X, Y, Z, the letters are arranged in the same way too, right? So this is the x-axis, that's the y-axis. In that case, the z-axis is this. Okay. So in that case, the unit vector along this one, cross the unit vector along this one is going to give us the unit vector along the third one. So that's the convention in here. All right, that's the one that we are going to apply. So do we choose always or usually? Let me say it like this. If in your application, you're going to use a cross product, there are some physical applications where you need this. I mean, this is something that you should know. Like, I mean, when you're talking about magnetic fields and when you see the formulas of physics, you're going to understand in which places. So if you're using the reference frame just to express the positions of some, I don't know, objects, probably you don't need to use a right-handed frame. You can also use a left-handed frame for that purpose as well. But if you are using a right-handed frame, then you have to choose, sorry, if you are using a cross product in your application, then you have to choose a right-handed frame, because this is basically related with this fact So as a result, so if this has to be true, then you have to choose a right-handed frame. So this is something that you have to be careful with, right? There's one other thing that I didn't mention about this convention. Okay, let me quickly do this. So there is a standard convention that people use for expressing the vectors which are pointing out of the screen and into the screen, or for you out of the screen and into the screen. All right. So the picture is something like this. So we have this analogy in here. So we just think of the arrow as a physical arrow. All right. So that means if you are looking at that arrow from this point, for example, I mean, this is you, right? Let's say it like this. This is you. In that case, what you do is like, you're basically seeing an arrow which is coming towards you. So what you are going to do, going to see is this. You're not going to see the whole arrow. You're just going to see its head with its sharp tip, right? So that's the sharp tip in here. But if you are looking at the arrow from behind, let's say it like that. In that case, what you see is this feather part in here. And I don't know, so some people thought that the feather part basically looks like that, okay? So as a result, when I'm going to express a vector which is pointing out of the screen, so let's say vector pointing out of screen, right? I'm going to express it like this. So I'm going to use this notation. So that's a vector pointing into the screen, right? At this point, we don't need to use these. Xbox, yeah, I don't know, X-Men logo also. At this point, we don't need to use it, but whenever we need to use this cross product, in that case, we're talking about some pictures in 3 dimensions. Since we cannot draw these perfectly on a 2-dimensional screen, what we can do is to basically use this kind of annotation. Okay, so let me then talk about the XYZ framing here in that perspective. So let me do it like this. So this is within the screen. So let's say XY plane is the screen plane. Let's say for that case, if x-axis is like that and the y-axis is like this, in that case, the z-axis is pointing out of the screen. Okay, so that's a right-handed frame. Okay, but you can also choose, if you want, if you insist, a left-handed frame where if x and y are in the same directions again, z might be pointing into the screen now. So that would be a left-handed frame. Okay. What we are saying is that don't use this one, all right? Use this one. So let's say, let's put a check mark in here, because only in that one, then you will be able to say I cross j is equal to k. That relationship will not be valid in a left-handed frame, all right? That's one of the important things, okay? I don't know if you have any questions in here. Let me go back then to this one, right? Cross products of Cartesian unit vectors. I think I'm going to draw the same picture again, or let me do it like this. How shall I do this? All right, sorry. I can use the advantages of technology. Sorry. Yeah, whatever. All right, let me do it like that. Okay, so here, therefore, I cross J is equal to K. So that means J cross I is equal to minus K then. Now you can go further. You can see that J cross I, you can use the same kind of argument. So the J cross I is also a unit vector because of the sine theta rule and whatever. And it has to be perpendicular. Sorry about this. When you are computing J cross K, you can actually use the same argument. So the result is a unit vector because of the magnitude rule. And because of the direction rule, it has to be along the x direction or minus x. So this is either plus I or minus I, and you have to use your right hand to determine which one is which. So in this case, it appears to be I. So therefore, K cross J is equal to minus I then. And similarly, K cross I is equal to J. And so therefore, I cross K should be equal to minus J. Okay. So I think part of the rule is very simple. Cross product of a unit vector with itself is 0. Cross product of two unit vectors gives us the third unit vector, but there is a plus or minus 1 sign in front of it. So that's the one that is kind of confusing. So in that case, what we are going to do is to use the cyclic rule, right? So basically, the idea is that, I mean, this is something that you can do it like this. So you just write IJK on the corners of a triangle, something like that, okay? So there's some kind of an order between them. There is an alphabetical order, right? IJK is written like that. You just follow that order. But these actually form some kind of a cycle in here because you have written them down like this. And so therefore, this is essentially a cyclic order. So IJK is in cyclic order. Or you can start with J. JKI is also in cyclic order as well, right? It's in the correct cyclic order. So for the products in correct cyclic order, the sign is +1. Okay. These are products in anti-cyclic order. Right? In which case the sign is -1. Sign is minus, right? Let me try to explain it like this. So that's an example. I don't know how to write the example in here. So let's say it like this. So I'm going to start with a product in cyclic order. So for example, I would like to know what K cross I is. Okay. So it is either plus J or minus J. So I would like to determine which one. I don't know which one it is. So what I do is I just write these letters, Kij. Is Kij in cyclic order or not? So if I start with K and then go to I and then go along with J, so I basically follow some kind of an order. And that order is the same thing as this order in here, right? It's the arrows in the same direction. So therefore this is in cyclic order. In which case, then I say that, well, plus sign is the correct sign. Okay. So what happens if the order is anti-cyclic? So let's say start with J cross I, for example. I mean, I know that this is anti-cyclic, but let's continue with this. I know that this is either plus or minus K, but I would like to determine the sign. So I just write J, I, and K. So what I do is this. So let me then erase this picture in here, right? So I start from J, move to I, and then move to K. So I'm following an order in here, but this is opposite to the cyclic order. So therefore, this is anti-cyclic, right? which means that the sign is negative. Okay. I mean, this is the only thing that you have to keep in mind. I mean, after a few exercises, you get used to this calculation. And so as a result, you can do all the possible calculations. Yeah, I didn't say this, but yeah, multiplication with a scalar is commutative, right? Yes, you can write down the numbers everywhere. So you can move the numbers anywhere you want, no problem with this. Clockwise, or it's not clockwise or anti-clockwise, it depends in which way you write these things in here. Yeah, if you write in clockwise order, then yeah, you can do it like that, okay? But it's called the cyclic order because they actually form a cycle. I mean, after K comes I, so it's actually a cyclic order in here. So you can think of it as like an ordering of people around a round table, right? So there's a table in here. This is a table, and then you place people around this table, right? In that case, there is no starting point and ending point, but there is an order in there. To describe the order in this kind of a situation, we call it as a cyclic order. So as a result, I mean, the person to your left, for example, might be next, the one after you, but there's some kind of an order in here. So we just describe that order as the cyclic order. So in the case of 3 people around the table, there are 2 possible ways that you can seat them, all right? And one is in the cyclic order and the other one is in anti-cyclic order, okay? In any case, so let's continue then with this. So if I have 2 vectors then, let's say A, I don't know, I'm just going to write it down like that, 2i minus j, and let me write B as 3i plus 4j plus 5k, let's say. I mean, these are 2 arbitrary vectors. Then I can compute A cross B. Okay. How? Because, well, I'm just going to use the distributivity. So let me do it one by one in here. So there are 6 terms in here. Luckily, not 9. I mean, if you do this calculation for the first time, probably you need to write down all the possible terms in here. But after some point, you may actually get used to this and then do this quickly. So let me quickly do this. So I'll start with the product of 2i, right? So I can get 4 times I cross I, and then 8 times I cross j, and then 10 times I cross k. Sorry, this is 3i. Thank you. So that's 6, and that's k. Okay, so next, I think the rest is correct, right? All right. So, and then we have minus j, so minus 3j cross I minus 4j cross j minus 5j cross k, right? So that's the expression, right? I'm using distributivity in here, right? I just distribute the product over the addition. And then we just note these. So I'm going to use a different color now. So let me use pink, for example. I just noticed that I cross I is equal to 0. And j cross j is equal to 0. So probably I didn't need to write this thing down because I knew that at the end, these would be 0. So then to determine the other one, so I know that I cross j is equal to either plus k or minus k. But this is something that's kind of the easiest one. Ijk is in cyclic order, so therefore the result is k. How about this one, ik? Well, I need to determine if ikj is in cyclic order or not. It is not, because ijk is in cyclic order. If you just change the places of two of these symbols, then you just change the order basically. So therefore, that's going to give me minus j. Okay. So j cross I, jik is in cyclic or anti-cyclic? Well, it is anti-cyclic. So therefore, this is minus k. And j cross k, well, that's cyclic. So therefore, that's equal to I, right? I mean, you need to do lots of exercises to actually get used to this, but I'm just going to write this thing down in here. So I'll start with this one. I get minus 5i. I have minus 10j. And then I have plus 8k in here and plus 3k in here, plus 11k in here. Okay. I don't know if I have done everything correctly. I might have made a mistake. Well, I can check this, right? So for example, check. Let's say, is A cross B indeed perpendicular to A? I can easily check this by taking a dot product, for example. So, I mean, that's one of the things that you can quickly do because taking the dot product is very simple. So let me do this calculation. Take the dot product with this. So this is minus 5i minus 10j plus 11k. A is 2i minus j. So that means it is 0k. So all I need to do is to basically take the corresponding components and multiply them together. So I'm just going to do it in here. So that's minus 5 times plus 2. So these are the products of the x components. And the y components have products of minus 10 multiplied with minus 1. And the z components have a product of 11 multiplied with 0. So I get minus 10 in here and then plus 10 in here. So that's equal to 0. Yes. So only the dot product of mutually perpendicular vectors is equal to 0, or one of the vectors is also equal to 0. That also may happen. I mean, since both of these vectors are non-zero, their dot product equal to 0 means that the angle between them is 0. So I can also check the same thing with the B. So is A cross B perpendicular to B? I mean, A cross B is supposed to be perpendicular to both A and B. Let's check the situation with B. A cross B dotted with B. So let me quickly write this thing down and minus 10j plus 11k cross, dot product. Dot, I think this was 3i plus 4j plus 5k. So as a result, this is minus 5 times 3 plus minus 10 times 4 plus 11 times 5. Let's check this. So that's minus 15, minus 20, and then plus 55. Minus 40, right? Okay, so I got kind of excited. All right, so yeah, it is equal to 0 again. So yeah, it checks. So probably our calculation is correct. I can also check the magnitude, but it's a little bit difficult to check the magnitude now. Yes, we can use the matrix way. you can use determinants to compute the cross product. It's something like this. Using determinants to compute cross product. It's something like this. Well, determinant is basically determinant of an n by n table of numbers. Right? It's just some kind of a table in here. So there are some numbers in here. Yeah, let me just do it 4 by 4. So what you do is, I mean, in a 4 by 4 table of numbers like that, people usually show the determinant like that, but let me also write a determinant in front, because we can use this symbol to express a matrix as well from time to time. So as a result, I'm going to do this. So the determinant of a table of numbers is a number that depends on all of these numbers. It's just computed in a particular way, okay? So what happens is that there's some kind of a recursive definition in here. So what you do is usually, I mean, if that, let me call these like, yeah, let me not undo this. So how we can compute it? So for a 1 by 1 table, that's very simple. So let me use this square braces in here, right? So I'm going to use the matrix notation. So the determinant of a table, 1 by 1 matrix is just that, right? That number in here. A determinant of 2 by 2, let's say A, B, C, D. 2 by 2 matrix is obtained by first multiplying these diagonal elements and multiplying these off diagonal elements and then subtracting these two. So that's basically A times D minus B times C. Now for 3 by 3, it becomes complicated. So what happens is this, there's some kind of a recursive rule in here. So let me actually kind of show it like this. So let's say that this is A, B, C. That's X, Y, Z. Let's say this is P, Q, R. Okay. What you do is this. You just take either a row or a column like this one. You can also choose the second column, but I suggest that you just choose the one of the columns, one of the rows or whatever, it doesn't matter. So let's say that you choose the first column in here. So what you do is this, you first write down these entries in here, A, B, and C. And then next to this A, for example, so let me come back in here, let me erase this. So A is an entry in here. So you basically eliminate the row and the column that A belongs to. So you are left with a 2 by 2 table, and you just write down the determinant of 2 by 2 table, right? So that's Y, Q, R, Z. Okay. So there's a plus or minus sign in here, but I'm going to explain this in a moment. For this one, yeah, let me place a space in here. Sorry about that. Yeah, let me write B in here, right? And then C in here. So here, for the case of B, yeah, I made a mistake in here, right? So what I do is I basically eliminate the row and the column that B belongs, all right? And then I'm left with a table. So in that case, this is like X, P, Z, R. And for C, I eliminate this column and this row, and I get X, P, Y, Q. Okay. So that's the recursive way of actually computing a 3 by 3 determinant. You just write it in terms of 2 by 2 determinants. Okay. It is not done yet. There are these signs of these coefficients in here, and they actually go alternatingly. So we start with the plus sign. This is negative, and this is plus. Okay. But it appears that each element in here has a sign. So this entry has a plus sign, but the next entry has a minus sign, and this entry has a plus sign, and so on. So it appears that, I mean, instead of expanding in place of the first column, you expanded around the second column, you would have started with a minus sign. Okay, so there are these signs in here that you need to be careful with. The rest is kind of straightforward, right? You then compute this, like the result would be A times YR minus ZQ minus B times XR minus PZ, or whatever. I mean, let me not write everything down. Okay, so that's basically the procedure. So I don't know. So later you are going to learn about the determinants. So let me just give some examples. So the determinant of -5 is -5. So the determinant of, let's say, 1, 2, 3, 4 is 4 minus 6, that's equal to -2. And the determinant of, let's say, 1, 2, 3, 4, 5, 6, 7, 8, 9 is, there are some other rules in here as well. So what I do is, like, for example, in that case, I'm just going to expand around the second column, all right? So I just write down these entries in here, the 2, 5, and 8. And I place the signs. So in front of 2, I'm going to write -2 and plus and minus in here. So these go alternatingly. And then I write down the determinants in here. So for 2, I'm going to drop this row and column. So it's the determinant of 4, 6, 7, 9. And this is the determinant of 1, 9, 1, 3, 7, 9. And that's the determinant of 1, 3, 4, 6. Okay, so I don't know, let me not compute this. So that's the determinant. Again, it has no physical or mathematical meaning at all in here. So you're going to learn about this later in linear algebra. These are actually used in solving linear equations, right? You're not familiar with this, right? I know that this is the case. I know that this is so. If you don't understand this, then don't use it, okay? Please don't use it, because that's going to be extremely confusing. But I know that some of you have learned about this, and some of you, they actually learn in the wrong way, okay? The problem is that they have just determined some kind of a structure for determining the determinant of a 3 by 3 matrix in some particular way. This is kind of wrong. But in any case, so what we do here is this. So we said A was equal to 2I minus J. B was equal to 3I plus 4J plus 5K. Okay. So when we determine when we evaluate A cross B, we take the determinant of this table. So first, in the first row or the column, doesn't matter, we just write down the coordinate unit vectors, I, J, K. In the second column, I write the components of the A vector. Okay, so let me just write it down like, yeah, why not? Let me first start doing this. In the third one, I just write down the components of the B vector. And usually expand around the first column, usually, but I mean, that's up to you. So in this particular case, that's the determinant of I, J, K. The first row, second row is 2, minus 1, 0. And the third row is 3, 4, 5. Okay. So I can see that if I expand around the first column, sorry about this, around this is basically I multiplied with the determinant of this 2 by 2 block, which is -5. And then I have a minus sign here, minus J. So in that case, when I erase this, I get this block in here where the determinant is 10. So I'm just going to write 10 in here. And then there's plus k in here. And if I eliminate k, then I get this 2 by 2 block in here. And the determinant is 8 plus 3, 11. Right? It's basically the same calculation, but I mean, you can do it in a more structured way. Okay. So if you are used to computing the values of determinants, you can use this technique. If you don't know what determinants are, forget about this, because that would be extremely confusing to you. Because, I mean, it's just for computing a very simple thing. So later when you take the math 260, you're going to learn about this. You're going to learn how it is used. It's basically used to solve linear equations, a system of linear equations. 260, yes. In the solution of linear equations, the determinant is actually quite useful. Later, we are going to see how you will also see, we will also see some other mathematical uses of the determinant later, right? But right now, if you don't know anything about this, then don't learn about it. It might be a little bit more efficient if you know how to compute it, if you are experienced in using the determinants. Doesn't matter, actually. So the other one is also good too, but you're not used to it. That's the only problem there. Okay, so we have spent so much time on this. So let me give a break and we will continue at 9:45. I think I'm going to give one more example. It's just computing the area of a triangle. Why not? But on an XY plane. So I'll tell you what to do about it. Okay. And after that, I'll just go to the kinematics part. Okay, let me stop the recording.